So, hi everyone. Good evening for all of us who have joined us this evening for energy in chemical reaction. So, Anshumala ma'am, as she was explaining that how this is more of foundational topic related to basic concepts. So, yes, this is energy. I guess all of you and all the people who are in sciences, we have heard about energy in different contexts. In physics, we deal with energy terms in a bit of different way than in chemistry. It comes in chemical reactions, of course, and others. Then in biology, there is energy itself, but that's also a bit different. So yes, energy it's kind of a part of science, but usually what happens is there is a disconnect between the streams. So if you talk about energy in physics, that's taken a bit differently. Then in chemistry, it's somewhat treated differently, and then biology again. So with this disconnect, there might be many misconceptions that comes into the picture. So this session or this more of a dialogue or discussion, it's designed to make an effort so that if there are any misconceptions, we can go. We will be discussing all those. The things will be very basic, and as some of you know, we at JLF we try to include as many questions during our sessions as possible. So here also, this is the dialogue. I'll be asking simple questions, very simplest ones, and if you will be going in the direction with me, following the conversation. But yeah, it's not listening to the conversation because this is not a lecture. This is the dialogue. So more you will participate in the dialogue, more you will be taking the queries and answering. So it will go very smoothly. And if at any place it feels like there's a confusion about the question or anything, you can put in the chat or you can just unmute yourself and you will go. Okay, so let's start. So first of all, which was the first metal to be used widely by early? So like in history, some of us or many of us has took it in schools. Maybe we have been to museums. We have listened stories. So what do you think? Which was the
Iron, ma'am.
first used? Sorry. Okay, we I'm getting in the chat, but someone was
Iron.
okay. There is copper. There is iron. There is zinc or copper. Okay, great.
Iron.
Yeah. So one which was widely used and first, like obviously there were metals, but usually we can say this copper. Yeah, along with copper, there were others. Like you said, there was iron, there was silver, there was gold, there was mercury. If we'll go to the museums, you will find kind of jewelry pieces, kind of tools which were made of these metals. So, were these the only metals that were present on Earth at that time? Because these were the kind of widely used. So, were these the only metals? No. Okay, no. I'm getting quite no
No.
in the chat. That's right. These were not the only ones. There were other metals also. Then how these metals like copper, iron, or lead, or others like these, how are these different from the rest of the metals? Like for example, sodium. Because these metals could be found or they could be used even by those people who had just stones and fires, like around them. They didn't have kind of this much technology as we have today. So they just had fire, they had
Oh,
stones.
teachers, sorry, Preeti. Teachers, please, right now, please concentrate on the interaction. That's why we don't like giving certificates and all. Now everybody is putting their addresses, and it's disrespectful to the resource person. She's asking and she's presenting something. So please concentrate there. We'll take your addresses. Don't worry.
Okay. Okay, so I'm getting answers. Native state, native. So, what do you mean like a native state? How do we say, okay, these are native states? Like there are other metals also. These are moderately reactive. Okay, yeah. So, as
Shalini also said noble.
okay, we had noble also. Noble metals. Okay, so usually noble is used for gases, but somewhat like noble also we use when the reactivity is like not there. So as many of you have answered, these are not unreactive, but yeah, they are less reactive, very low reactivities. They're okay, malleable and ductile. So these are the properties, but many other metals also had like these properties, and this is not the reason that we started with just these metals. Uh, will you be providing a copy of the presentation, or do we take notes? I will kind of suggest maybe that if you will have a pen and paper with you, that will help during the kind of session, as we'll be going through questions, and there'll be later on for some exercise also for you people to do. So that would help. Yeah. They are found only
We
in combined
can,
form like
can
chromium.
provide the PPT, but not as in a PPT format. We'll provide it as a video later in the
Yeah.
WhatsApp group. Yeah.
And this session is on YouTube also, so you can go through it again. You can view it on YouTube. Shalini Sharma has raised her hand. Yes, Shalini ma'am.
Good evening, ma'am. Okay.
Yeah.
What is the issue if I call it a noble gas? I mean, noble metal. Okay. Because normally I understand anything which does not react, okay, can be termed as a noble. So, like when you're talking of gold and platinum and all, okay, I'm not saying they're inert. Okay. So I'm saying they're noble. So,
Okay.
is this scientifically correct, or there is some gap in my understanding? Please. Thank you.
That's fine. Shalini ma'am, so if we are talking about, can we call these metals as noble, or is there any issue with that? So I would say, like, if we go into terminology, then there are many things that you can call this metal. You can say noble, like for even gases, there is noble, there is inert. So this is just terminology. But what we are trying to kind of capture here is that these metals are different from the rest. Like there is kind of, we are comparing the two. So I am not asking for a term, okay, how will you define these metals? We are just looking for the properties which differentiate these metals from the rest. And because of those difference, because of that property, they could be found even with the kind of fire. They didn't need much advanced technology. And for that,
My understanding, noble is generally not used for metals, right?
yeah, we don't use, but the thing is, I am not trying to get into, okay, is this scientifically correct or not, because that way, like, this is not related to the session, so we are not going
Yeah, no,
haywire.
that's okay. But she asked, so you have to address that. So,
Yeah,
okay.
this is used for gases, but not for metals. We don't use noble kind of category. Okay, these metals are or inert. Okay, then we have more answers. Different chemical, physical. Okay, less reactive. Yeah. So these metals, they can occur in nature in their pure form, and yes, as many of you has replied in the chat, these are less reactive metals. So this is just another example. So if you have sodium and there is gold, so many of you even might be wearing gold. So what if the two metals are kept in open, like in the air? What will happen? Something will happen to the gold, something will happen to the sodium, or nothing will happen.
Gold is
Sodium will
not reactive
fume.
and it cannot react with any of the other substance, but sodium is very reactive. It violently reacts with air.
Okay, so sodium will react, but gold won't react. It will remain.
Will not react.
Yeah.
And actually, Vazida has said alloy formation. Vazida, do you want to clarify actually what you mean by alloy formation?
Okay, she has put in the
Alloy
chat.
is simply the mixture of metals and non-metals, or metals with other non-metals, in order to make it corrosion resistant and addition of other more properties to it.
Okay, we were still talking. Okay, that's fine. But are we following this? Like, are we clear about this? That there are few metals which are less reactive and they could be found, and there are metals which are more reactive. So we are just comparing the reactivity. Okay. So if you see, as someone has put in the chat also, that sodium, if it kept in the air, it forms like sodium oxide. So even if you just take a kind of fresh piece of sodium metal, it's very soft, it can be cut. And if you cut, you will see there is shiny kind of surface. But in a few kind of time, this shiny surface again it turns gray. So why does it turn gray? Because it reacts with oxygen and it forms sodium oxide. Yeah. Okay. So for the reaction, we have this equation that sodium plus oxygen it gives us sodium oxide. Right. So again, if I ask you why is it that sodium reacts so quickly but gold does not?
It is because of the valence shell electron. They have one electron which can be easily, shared.
Which can be easily shared. So 4 electrons usually it comes in the kind of the first your column, and because of that these are highly reactive. So in the simplest term, if we compare the two, we can just say that yeah, sodium this is highly reactive and gold it's not that much. Yeah, so we are not going into many more terms. Okay, there are this the reasons would be many. You can write many statements, but in simplest one we can just say that if we compare the two, the sodium is more reactive and gold is not. So because of this kind of high reactivity is kept in kerosene also, it can't be put in the air as we have seen, it will react. It can't be put in the water. It has a kind of explosive reaction there also. So what is this chemical reactivity that we are talking about since kind of beginning? Okay, this is less chemical reactive, this is more reactive. So what do you understand by reactivity? Chemical reactivity.
Ability to get combined with the other substances.
Its ability to get combined with others. Okay. Bonding with other substances. Okay. There is urge to have stability. Okay. Reactivity series. So
Its tendency to
Gayatri ma'am, you were
its tendency to get a completely filled shell.
Tendency to get completely filled shell. So yeah, like as you just saw, for reactivity also we can give many definitions, but at the side of simplest language, we can say it's a tendency or the ability to get chemically changed. Yeah, like that we are having many rearrangement of atoms, ability to donate or accept electrons. So all these comes later. But if we just start with, then we say it's a tendency or ability for any element to get chemically changed. So what is the meaning of tendency? If we trying to explain, okay, what is tendency? So we can say tendency is kind of a natural behavior of something, of a person, of a thing. That how it will naturally behave, that we call it tendency. So what would be the natural behavior or what would be the tendency of this imbalanced pile of stones? So there is a pile of stones kept, like stones are kept over above each other and it's imbalanced. So what will be the tendency of it? What will be the natural
Fall. Fall.
Balance. That's why it will fall down and it will kind of get a balanced state. So if you will see around you in nature, you will find like everything, if there is an imbalance, so nature is trying to move it towards balance. So what it is actually trying to achieve by moving from imbalance to balance?
Equilibrium.
Equilibrium. Okay.
Stability.
Stability. Yes. So this also
Less energy state.
Less energy state. That's right. So if there is an imbalance, so the nature also tries to move towards more stability.
Stable.
If you compare these three examples, like there is a ball on the ground in the first one, in B case, it's kind of having small jumps. Then in the C, there is ball with high jumps. So which one would you say is the most stable one?
Ball on the ground.
Ball on the ground will be the most stable one. I guess all of us agree with that. Great. So now, which one of these would have the most energy?
C.
C.
C would have most energy. That's right. Great.
C.
So with these two kind of statement that the first one was most stable and the last one had the most energy, can we say
Less
there is a
energy, more
relation between
stability,
stability
ma'am.
and energy? Okay, yeah, I'm getting in the chat. Energy and stability have inverse relationships. Less energy, there'll be high stability, more energy, less. Yeah. So if there is less energy, more stability, and there is an inverse relation between the two. Great. So based on this, what can we say? Which side of this reaction that we saw earlier, the sodium and oxygen, which are reactants, so left hand side, and then they are making sodium oxide. So which side from these would be more stable?
Product
Right
side, ma'am.
side.
Right side.
Right side would be more
Right side.
stable. So
Sodium
that's
oxide.
how it's going towards the right. This is kind of a natural behavior. We are not doing anything. It's just sodium is kept in the open and it's naturally forming sodium oxide. So it's what's more stable. And if we talk about energy, which side will have more energy?
Left side.
Reactant side.
Left side.
Reactant.
Reactant side, like side.
May I interrupt and ask a question, please?
Yes, Shaleen.
Sorry, but then see, this is only with respect to sodium. We know this is a very simple reaction. Now, but if there is a reaction which is very complicated, say KMnO4 and HCl, okay, is it easy to interpret? I mean, unless you know whether it's an endothermic or an exothermic reaction, is it? Can you merely look at the reactant or the reaction and say that the products will be more stable or the the reactants will be more?
All right. Shalini ma'am, we will be coming to those points also towards like we are moving towards that.
Thank you. So sorry to interrupt. Sorry.
That's fine. That's fine. So this is yeah, these are like just things we are trying to connect to each other. We are moving kind of slowly, taking one step after another. So far it's just stability and energy. So if something is kind of naturally happening, we say it's more stable. And as we just established, okay, the energy and stability are inverse relations. So we can say this an estimate, okay, so this should have more energy. Great. So what kind of energy is this that determines the reactivity? Like if there is some energy is involved, we are saying this is less energy, this is more energy, and this is more stable, this is less stable. So what kind of energy is this? This is determining the reactivity. So if we talk about energy, what are the commonly known forms? Like in other aspects, you must have heard about some forms of energy. There is kinetic energy, chemical energy, okay.
Rotational energy, vibrational energy.
Kinetic, potential, tidal, solar.
Ionization energy.
Heat energy, electricity, a number of forms of energy which we have heard of. So they like the common ones which I have taken over here are potential, kinetic, heat, electricity. But as you said, there are many others.
Internal energy.
Yeah. So for energy, we have found so many terms and names, just the forms of energy. Yeah, that's right. So let's here we will just discuss a little bit about potential energy. Yeah. So let's try to understand this potential energy with the help of two magnets. Usually, if you are kind of doing this with students, it would help if they have magnets in their hand. If you are also have, you can also do it side by side. I have used animation, so I'm hoping it will be clear with that. So let's try. So what will happen if we take opposite poles of two magnets and they are placed close to each other? Opposite poles of magnet close to each other. What will happen?
They will attract each other.
Attract each other. So they will.
There will be attraction.
Yeah, there will be attraction. So as you say, if they are opposite poles, they will attract. So they will move towards each other. There will be a movement. So they are just magnets, simple magnets you have taken. The opposite poles, they will move on their own towards each other. So we are seeing some movement over here. Similarly, if they are similar poles, they are kept close to each other, what will happen?
They repel each other.
Yeah.
Repel. They will repel each other.
And they will move away from each other.
Move in the
So
opposite direction.
some movement here. If they are kept kind of close to each other, if they are similar poles, they will move away. So there is movement again. But what form of energy is associated with movement?
Kinetic energy.
Energy.
Kinetic energy. Yeah, there is some kind of kinetic energy in these magnets. They are moving towards each other, moving away from each other. It means if there is movement, there is kinetic energy. From where this kinetic energy came?
From the movement of the atoms.
From the movement came the kinetic energy.
Motion and
It was actually there as potential energy. Due to its movement, the potential energy changes into kinetic.
That's right. So energy, as we all of know, like can either be created nor destroyed. It can just be converted. So it means there should have been some energy which is now converted to kinetic energy.
Converted.
And what form of energy was already there? As Gayatri ma'am said,
potential energy.
Potential.
And as we had taken magnet, so we just name it as magnetic potential.
Magnetic potential energy.
Okay, great. So are all of us on the same page over here, or is there any confusion in this? So there was magnetic potential.
Yeah,
Now,
I just want to add one thing, Preeti. See, it's like for teachers, it's a very good device to give children. How do you recognize potential energy? The moment you release something and it runs, then it must be having potential energy in the initial state. Something which is bound, which is okay, still, but in a special configuration, in a situation, some situation. But how do you recognize that it has potential energy? As soon as you leave, it will run, which means the energy will change into kinetic. So how to recognize potential energy? Potential energy is a hard one. How do you recognize it? Release and it runs. It's a wonderful what should I say trick to give to children, right? Okay, Preeti, carry on.
Shalini ma'am has raised her hand. Yes, Shalini ma'am.
Yes, okay. It's a very stupid question, but I'm just asking, like within an atom, there are loads of energies, like you translational, you say rotational, nuclear and all, okay? How do I know that it is only the potential energy, okay? I mean, like releasing is okay, but then nuclear energy is also holding the atom together and all, okay? So how is it that we are so sure? I'm sorry, I'm again saying it's a dumb question, but then how is it I'm so sure that it's only the potential energy which is getting converted to the kinetic energy? Is my question clear?
If I am kind of getting you right, then it means you are saying that in magnets, like there are atoms, there are so many energy. So their
Correct.
energy would be there, but how are we saying that this is potential energy?
Yes.
Okay, right. So, ma'am, as I would say, like for energy, we have given different names. It's just okay if there is potential. Like I will just discuss it after this. So, what energy form do we call potential? So, potential energy is something that will appear only when given a chance. There is a kind of potential, as you say, okay, you have potential to do this. If you will do, you have potential of doing something. You have potential energy that can be converted into another form. So now this potential energy usually, as we see like in many examples, it usually gets converted into kinetic energy, as Anshumala ma'am said. So it's Shalini ma'am, you are saying something? Okay.
Sorry.
So Sapura Pega ma'am, she has said in the chat, stored energy. You can say that also, like it's stored, and when it will given chance, it will be kind of released, it will be converted into some form of another energy. So this is just
Preeti, I'll just add this only for Shalini also. Ma'am, the simple thing which Preeti is saying, which I am saying is, whatever it is, wherever you are seeing movement already happening, that's kinetic energy. Anything, whether it's inside nucleus, outside nucleus, whether it's electrons, whether anything at all, anything which is already moving is kinetic energy, has kinetic energy. But anything which moves upon release, which moves in the next stage upon release, that has potential energy, which Preeti is saying, it has potential to move, right? When we say it is potential energy, which means it has potential to get converted into kinetic energy, or in other words, it has potential to move. It will move the moment it gets a chance. That's what Preeti has been trying to say. Yeah, Preeti, please carry on.
okay. So we are talking about potential energy, and yeah, as I'm just explained. So potential energy is usually associated with position, as kinetic energy was with the movement. So it comes with virtue of position, and where the position should be, it's in a force field. So now this is kind of another term which we use quite regularly. But if we go for like the at the student level, so usually it can there can be some confusion. Okay, what is force field now? In which force field they will be positioned, that will give them potential energy. So just to explain a bit about force field. So this is the reason around an entity. If there is a magnet, then there'd be a reason around this magnet where the influence of the force can be felt. So usually we do this with magnets and the iron powder. You can do like this also. So you can clearly see there are some lines. So only around in some reason the force can be felt, and that will be the force field of this. And in this force field, if you put an object, so based on the position of that, there will be put a kind of certain amount of potential energy in that. To make it more clear, let me just ask you. So if you are lifting a ball from the ground, so what is the force against which you are kind of taking it away? You are putting potential energy.
Gravitational
force.
Gravitational.
Right. So that is gravitational force. So till there is a point, like for Earth also, it have the gravitational force can be felt up to some reason only, and based on the position of an object in this, there will be the potential energy kind of quotient. Okay, this object it is this height, and that's how it has this much potential energy. So again, coming to the Dori, you have raised your hand.
You're saying that there must be a force field for potential energy to be stored in an object. But when, for example, when we stretch a spring, then there's no force field, but some kind of potential energy stored in it, because when we release it, it tries to get into its original shape.
Okay. So if I'm right, so I would say that for a spring also, it will depend that how far you are stretching it. If you are stretching just a little bit, so that much energy would be there. If you are stretching it a bit more energy would be there, potential energy. If you are stretching a bit more, so you will see there is a kind of distance is playing some part into there also.
But there's no force field, right?
See, Dori, we have these non-contact forces, and they make fields, which means electrical, magnetic, gravitational. They make fields. Contact forces don't make fields. And in a spring, actually, it is spring's own internal forces, which is actually because of its arrangements of its atoms and all that. But they're not. Okay, we can call them field forces only if you are able to see the spring's own atoms and molecules and how they are all electromagnetic forces actually. In a very true sense, what is happening inside the solid is the attractive forces inside a solid are also electromagnetic. But you won't be able to see that field existing there, right? Okay.
Okay. So with this, can we say which one of these are gaining most height? There's ground, there's small, then there's height. Which has the most height from the ground?
C.
Okay, Anshumalam, there is a question in the chat. Who generate these field and how?
So Ravi is here, so we are going to have a barrage of questions. Ravi, some patience, but yeah, okay. I mean, today we don't want to get into really force fields, but a very simple answer to your question is there are these 4 fundamental forces that we recognize in the world. They are there. They are just there. We electrical, magnetic, and gravitational, and then there are nuclear forces, and we recognize their presence as something which is given to us. I mean, with the world exists with these forces, so we don't say who gives them. We just recognize that, okay, okay, mass and mass will have gravity between them, like that. So, but anyway, I would request you to allow Preeti to be on her story. We will open up force fields in some other session. For all others who don't know Ravi, Ravi and Dori have been our favorite students who ask so many questions that sometimes we have to run away. But no, we are not trying to run away, but it's just that request is to let Preeti be on the today's story, right? Okay.
May I ask a question, please? I am equally sorry, inquisitive, but may I ask, please?
Yes, Shalini.
Okay, so my question is, like when we are talking of gravitational, so gravity pulls things towards itself. Okay, so by this logic, can we say that the gases go against the gravity because gases tend to rise up? They are not pulled inwards.
It's a very good question. But see, actually, gases are also pulled by gravity. That's why you have greater amount of air near the Earth's surface, and you have lesser. The density of air actually keeps reducing as you go up in height. So there's more concentration of air molecules near the Earth's surface. So it is because of gravity. There's no other reason. But gases expand because of their own movement. The molecules are in a huge motion, and gases molecules or their particles cannot stay in one place. So it's because of their own very nature and their internal energy and their pressure. Pressure, by the way, is also a form of potential energy. I know I'm opening up a can of worms by saying that, but okay, let me not digress. But yes, it's because of gases' own movement that gases expand and go away from wherever you try keeping them. They don't stay in one place. But yes, gases do experience gravity.
Thank you.
Okay, so moving forward, we just established that the third one, it has most height. So based on this, which will be having the most potential energy? The ball which is on the ground, then the ball which is kind of having small jump, or there is both high jump. Okay. Okay.
अच्छा अच्छा
Please,
ये काम रह गया
please mute your mic. Somebody's
Yeah.
Yeah.
Okay, so in this case, I'm having that ball in the ground would have the most potential energy. So I guess I can see we have some confusion. So in the earlier one, we established that against gravity, as more you will kind of work against gravity, the more energy you have to provide. And the last one, it is at the most height. So you have to kind of work more harder to take it to the higher kind of position. But now we are seeing some confusion that some people are saying the ball which is on the ground, it will have the most potential energy. Okay, so now the answers has been changed. So the ball which is having high jumps, which have the most energy. So is there any confusion for the people that whether A will have energy like most or the C will have? Or shall I move
Which
forward?
energy are you talking about? Potential energy?
Potential energy. So it's against gravity, so I can kind of simply ask which will have the most gravitational potential energy. C. Okay. So I guess now all of us are on the same page. We will have the most potential energy. So that was about gravitational. Let's take another example from magnets. So if they are opposite ends, so obviously they are kind of coming close, but we are trying to move them away. So which force is acting between the opposite poles of magnet? Opposite poles of magnets we have taken. Which
repulsive
force
forces
is acting between the two? Gayatri ma'am, you are saying?
repulsive forces.
Repulsion force between the opposite poles.
It is magnetic force of attraction, not repulsion. It is attraction. Now it is repulsion.
Now
It's
it
same
is
goals.
repulsion.
So then
Now
if
it
it's
is attractive force. Magnetic force.
Yeah.
So we'll say
So if opposite
magnetic
forces
attraction.
are taken, then it's magnetic attraction. And for attraction, if there is attraction between the two things, like for this case, they are opposite poles. So if there is attraction, so the most stable position for these two objects, for any which are being attracted to each other, would be to become closer to each other. And that's how they will have the least potential energy. The most stable, least potential for attraction, it will be as much close as they can. So if they're opposite poles, they will try to be close to each other. But in the opposite case, if they are similar poles of magnets, so which force is between them?
Magnetic force of repulsion.
Yeah. So now this is magnetic repulsion. And if there is repulsion between the two bodies, two objects, then the most stable position for that is to be far away. And being far away only, they will have the least potential energy. So there, like here, we are trying to bring kind of three things together. One is most stable, and when it will be most stable, then it will have the least potential energy. And for repulsion, it is to be far away. For attraction, it is to be close to each other. So they will repel. So this was kind of physics so far. This is how we take energy in physics, the magnets, the gravity, and everything. But in chemistry, we talk about atoms. So now there are no magnets, kind of these things over here. So let's see how we can relate the energy terms from physics to the chemistry one. So if two atoms are approaching each other, so what kind of interactions would be there between the two? So obviously, if they are approaching each other, so it means there would be some attraction between the two. So if we see there are two atoms, there is one nucleus, then there are electrons, there is another nucleus, there are other electrons. So which would be attracting which?
Nucleus of one atom would attract the electrons of the other atom and vice versa.
Yeah. The electrons of one would be attracted or would attract the protons or the nucleus of the another. In chat, I am having old bonds break and new forms. Neera V. Mohan, also, I like still for this point, let's try to kind of work together. Here, the question or the concept that we are trying to build is what happens when two atoms approach each other? What kind of interactions, what kind of attraction is there? So I am not talking about compounds. We are not talking about reactions for now at present. At the moment, what we are talking about is
Van der Waals forces of attraction, ma'am.
Then
also
there
be
is
repulsion, ma'am, between nucleus of one and the nucleus of the other, electrons of one and the electrons of
yeah, we will be coming to that. So as Doris said, in these, if there is attraction, though this is between nucleus and electron, but as we see earlier that if there is attraction, so the stable position for the two kind of atoms would be, what would they try to do if they are being attracted toward each other? They would be closer to each other. But does it happen? If there would be only attraction, then all the atoms should be touching each other because they are being attracted, and the most stable is for them to be closer. But does it happen? Or all the atoms touching? No.
No, it doesn't happen because the similar charges repel, and that is why they can come to a certain level only. Distance, yes.
Yes.
Both attractive force and repulsive force acts here, ma'am.
Yes, that's true, Bharti. So there is space between the particles. Why? Because as some of you have said, and I guess all of you will agree that there is attraction, but there is repulsion also. So where is repulsion? Like between what entities is there repulsion?
Similar charges.
Electrons.
So the electrons will be repulsion by electrons, and thus nuclear repulsion will be there. So there is attraction, then there is repulsion, and we just discussed before this that if there is repulsion, then the most stable position for the two objects or two bodies to have the least potential energy is to be far away. As much as far away they can be, that would be best for them. But then, like, there is attraction, there is repulsion, they want to come together, but they have to kind of stay far away also. So then what is the best way for atoms to have least energy? What should they do? So for this, we have taken a visualization, a simulation, to see how kind of two atoms come together, make a bond. Let me know if all of you can see this new screen that I'm sharing now. Okay, great. So here there are two atoms. One is this, one is this. The blue one is kind of positive and the electrons is kind of jumping around. Then there is another, two things are taken. For now, as you can see, there is written overall interaction is attractive. So at this distance or at this position, there is attraction between them. At the downside, you will see the graph for potential energy. So let's try to move one atom towards the another, as there is attraction obviously. So for attraction, it will move towards the another. As I'm moving towards the another, I guess all of you can see in the graph that potential energy is decreasing. It means it's becoming more stable. For attraction, it wants to be closer. It is getting closer. So it's becoming more stable. And for stable, its potential energy is decreasing and decreasing and decreasing. Still attractive, still attractive. Now it's balanced. So the potential energy has reached to this point. But what if I move it further towards the another element? As I just move a little bit, you can see now there is repulsive interaction overall. And the potential energy, if you will see in the graph, it has increased again. So it means if you will move more, the repulsive force is getting more and more between them. The potential energy has increased very much, which is like more stable. So for stability, the overall interaction has to be balanced only till this point. This is that position of the two atoms where the attractive and the repulsive forces are balanced. Are we clear about this?
Yes.
If there is any confusion,
Yes,
or
ma'am.
All good, ma'am.
all good. Okay. Anshumala ma'am, do you want to have a check now, or shall I?
Sorry?
Do you want to have a check now, or shall we move forward?
No, I don't have much to add. It's, I mean, if okay, Dori and Ravi, is this clear? I mean, what she's saying is that there are attractive forces also and repulsive forces also, and they reach one particular position where both balance and the atoms are at their lowest energy state. And that's their stable state. Yeah, so please carry on.
The potential energy is, ma'am, minimum and the net force is 0 at that position. They are neither attractive nor repulsive whenever the potential energy is minimum.
You can say forces are balanced. 0 is not.
Net, I mean, balance means net force is 0. Okay. Balance is the same thing. The same thing.
This is yeah. So that's how the confusions kind of start arising. If we will say, okay, there is no attraction, there is no repulsion, and now it's all balanced. So rather than that, we should say that there is repulsion, there is attraction, but now the forces are balanced in a way that it has the like whatever the possible minimum potential energy it can have. That's how the forces are balanced. But yes, the forces are there. Great. So let's move ahead after this. all the atoms or objects in nature or universe, they interact with others and try to minimize this potential energy. And why? To have maximum stability. So in chemistry, we call this chemical potential energy. Like we are talking about potential energy only. So for this, we have given this a term, chemical potential energy. And as we were discussing earlier, for potential energy, it comes with kind of position, how the things are positioned. Therefore, this thing only, it is decided how much potential energy they will have. So what are the positions in chemistry? So if you will have a look at a molecule, they will be spacing, the composition, the shape of the molecule, the bonds, the angles, everything. So all of these, they decide the result in a certain amount of potential energy. So every substance, every atom or ion or kind of a compound molecule, every substance finds its own most stable state where it has minimal potential energy. So if like for example, there is glucose, which has 6 carbon, 12 hydrogens and 6 oxygen. So all of these atoms, they are kind of arranged in a format where the bond lengths, the angles, the orientations, everything is in such a way that it will have the minimal potential energy and it will have a most stable state. So what will happen if we change kind of a bond length? Will there be a change? If we change the composition, if we change the spacing, if we change the angle? So yes, in chemical reactions, we do this only. We change the composition or the bonds are changed or the orientation is changed. And as soon as these changes are done, there is change in chemical potential energy. Okay, Shalini ma'am is asking. So does Na2 have higher entropy and
Shalini, I would request.
No, yes, no, I'm holding my question. Yes.
Yeah. But secondly, we talk about entropy of a system, not a single particle. It's like you are talking about Na2O and sodium and oxygen, but if you take a full system, it will go towards higher entropy. But then right now, let's at least talk about energy. We can't talk about all this in one go, right?
Okay, thank you. So moving from here. Yeah. So this I've taken like from a master's. So this is just a kind of relative. So the height of these lines. So like for the reactants, as you will see in the left side. So this height from the kind of bottom, it's kind of relative energy of the reactant. And towards the right, you will see some lines which are the potential energy for products. So these are just relative energy. So we do some calculations in the programs and then we find some values, then we plot it. So as you will seeing all these lines in between, these are just if there is any change in the bond length of reactant, so this will happen, this will happen. But for this discussion, what we will take into consideration is that there are reactants, these have some energy, this much, and relative to that, the product has this much energy, right? This height. So just the relative nature of the two. So based on this, what we can say, which one has more energy? The reactant has more energy or the product has more energy?
Reactant.
The reactant.
More energy. Okay, great. So the next question comes about stability. Which one is more stable? The reactant is more stable or the product is more stable?
Product is more stable.
Product is more stable. Great. So using this, we can also compare the two products. If they are kind of two possible products that can be formed from a reaction, and if we can see the potential energy of the two, so what can we say? Which product would be more stable? Product 1 or product 2?
Product 2. Product 2.
No, product 1 will be more stable.
Wait.
It has lower energy than
product 2.
Okay, so do we have like different votes? Some people are saying product 1 would be more stable. Anyone who is going for product 2?
I think Dori is saying
product 1, ma'am. product 1 due to less energy.
Yeah.
Got it. Okay.
Has lesser energy as compared to product 2. So that's why it will be more stable. Shalini ma'am is asking what accounts for the different stability of different compounds. So in simplest terms, I would say, Shalini ma'am, that as we just discussed, the spacing, the orientation, like every kind of thing about a molecule that decides how much potential energy it will have. So for these two products, we will say that product 1 is more stable. Great. So we are going, I guess, great so far. So now if you just see the reactants in the product. So reactant had this much energy, but product has only this much. So where did the energy go?
The
It is
energy
lost
gets
in the form of
released.
heat.
Yeah.
Lost in the form of heat energy, sound energy, light energy, ma'am.
Yeah. Surroundings. Okay, great. So yeah, in some reactions, it happens that reactants, they have more energy, chemical potential energy, and the product has less. And this kind of energy, it's released in the surrounding to the surroundings. And these are the exothermic reactions. So if we take this one, this case, this scenario that there is reactant which has less energy, but the product has more kind of chemical potential energy. So where this energy comes from?
From surroundings, it absorbs.
Yeah. So this energy has to be given, and this energy is used for the reaction to be carried out. And these reactions are usually called endothermic reactions. So exothermic, endothermic, I guess all of us have studied, and most of you would have taught also. So these are the two types of reactions.
Rupinder Garg said in breaking bonds. So Rupinder sir, actually we are trying to bring across this idea that energy does not lie in making or breaking bonds. I mean, like you see, in any reaction, some bonds would be broken and new ones would be formed. So
I will just stop you over here because we are like, we are moving towards that. So let's go stepwise. We will also go to the breaking of bonds and the making of bonds.
Yeah, correct. So that's what, see, because he said in breaking bonds, so I'm telling him that, I mean, that's
Yes,
not
ma'am.
how we are trying to look at energy, right?
Actually, excuse me, ma'am.
Yes, sir.
Actually, when we are dissolving glucose in water, or say, for example, dissolving sulfuric acid in water, there will not be any breaking or making, I think so, ma'am. They are just getting dissolved.
Yeah. Okay.
Will it be okay, ma'am? Is it correct?
Okay. So if you are dissolving something into like water, so is there any chemical reaction taking place?
If it is going to be an ionic compound, maybe some chemical reactions. But if it is a non-electrolyte like glucose or something, there will not be any chemical reactions going on, ma'am.
So that's, I guess, in some case you will see if you put something into water, the temperature kind of it increases. In some case, it decreases. So that's why we say, okay, the heat is kind of released, or so there you will see the kind of change in the energy. It's released to the surroundings, or it is taken from the surroundings. That can also happen. Okay. So here, this is just as a sign convention, like students, when they move towards the 11th or 12th classes, so they will see this plus 178, plus minus 890. So the energy change is given the numbers and with the sign. So it at times can become a little bit of confusing. So this is just to address that. It can help them to see that for which kind of reactions we use plus and for which reactions we use minus. So let's see what's happening for these two reactions. So if there is decomposition of calcium carbonate, and we are getting calcium oxide and CO2 for this. So the energy changes plus 178. For this reaction to happen, for this decomposition to take place, we have to heat calcium carbonate. It means energy is required released in this reaction. For this reaction to happen, energy is required or energy is released in
Energy
this.
is required.
Energy is required. In this. Yeah. So we are providing heat. We are giving heat. It needs energy, then only it will happen. So this energy, we can say that they are reactants. We added some energy to that. We kind of gave some energy and then the products were formed. So for you can make it kind of simplistic that an endothermic reaction, you can write that as that reactant and plus some energy and that will give products. So this plus sign, you can be kind of taken, okay, for the endothermic reaction, we use a plus sign and the plus sign shows that energy is taken. Similarly, if like in this case, methane, it is reacting with oxygen or it's burning. So this is kind of a fuel which burns. So when we burn a fuel, so the energy is required, the energy is released.
Energy released.
So for burning fuel, the energy is released. So can we just write it like this? That there were reactants, then there were products, and with products there were some energies also. It was released. So in I guess simple mathematics, if we apply, so for this plus 890 on the product side, we can just simply write as that reactants minus some energy and then we got the product. So from this minus, we can help the student to see that for exothermic reaction, we can represent that as reactants minus energy. So the minus sign is used where the energy is given out. Great. So if you see at the two graphs A and B, which one would you say that there is the negative sign?
A is exothermic.
A is exothermic. Lida ma'am, you were saying A is exothermic?
Is it correct, ma?
A is endothermic.
A is endothermic. That's fine. Lalita ma'am, can you just see and try to kind of elaborate that there is energies of the reactants that are this level and the products, the energy is this much. So the energy is more or less in the products?
Product has more energy.
More
Yes,
energy.
ma'am.
More
So
energy.
it has gained energy from surrounding, endothermic.
Okay, ma'am. Got it.
Judy, can you specify your confusion?
Yeah. So, if energy reactants, if the reactant product has more energy than reactants, it means the energy is being provided or released.
Okay. So if product has more energy, it means some energy was given to na. So some energy was added. So added means it has to be given. Then only it can be added and then we will have the product.
Then it means it's an endothermic reaction.
Yeah. So A is endothermic. As you can see, the product has more energy which is taken or given from the surroundings. And in B, the products have less energy than reactants. This means energy is given out. And so we will use minus sign.
But ma'am,
What makes some
will it
bonds?
be a feasible process, ma'am?
Sorry, sir, can you repeat?
Will this be a feasible one according to thermodynamics?
So yeah, we are not going to thermodynamics yet, but yeah. So for here, I guess all of us has got that how can we help students to see where to use positive, where to use negative. These are just sign conventions. But with this, I guess things will become more simpler and clear. Shalini ma'am is asking, what makes some bonds or compounds have more energy than the other? And Bharti ma'am is saying energy absorption is endothermic and positive and vice versa. Okay. So Shalini ma'am, what makes some bonds or compounds have more energy than the other? So again, I would go back to that what decides the energy, chemical potential energy, the position, the orientation, the bonds. So where like how it's kind of structured, how it's oriented, all the atoms and everything. So that will decide which will have more energy and which will have less. Okay.
May I ask a question, please? Sorry. But
Yes,
say, suppose it, I mean, do the energy of the compounds change in every reaction? Because some react in a certain condition, but it does not react with the same compound under some different conditions. Okay, so does the energy associated with the compound varies with the other reactant? Is it dependable on the other as well? Like
Okay.
supposingly when you say water, okay, and we dissolve. I'm not taking a chemical reaction, let's say physical dissolution, but some dissolution are exothermic and some are endothermic. But the water is constant. Water is the same thing. So does the energy of a reaction depend on the other reactant as well?
So the energy of a reaction will depend on the reactants or the kind of situations, conditions. Energy of a substance, like for water, if you will calculate the chemical potential energy, so that will have a fixed value. But when it will react with different substances in different conditions, then in those different scenarios, so what is the energy of the other substance, other reactant, if the energy is given, so that will decide the energy of the reaction.
Thanks. So it does mean that it varies with every reaction. I mean,
Yeah,
it is affected.
Yeah.
Okay, thanks.
Great. Okay, Dory, I didn't understand the question. Dory, which one? Like this one? Which one is on the screen? Depends upon the condition.
Yes, the one Shalini ma'am just asked.
Okay. So Dory, Shalini ma'am was asking that there is a reactant, for example, water. It has when it takes place in different kind of reaction. It is dissolving one compound in one reaction, another it is reacting with another. So the energy of the reactions are different. So would it be same?
I can't hear you properly because somebody has.
Okay, I think now it should be fine.
Yeah, now you're audible.
Okay. Sometimes happen. So like people are teachers. If you want to ask something, you can unmute yourself, but it would be helpful if you can mute yourself after that. It's kind of causing a bit of So Dory, shall I repeat the question or?
Yeah, no, I couldn't hear you.
Okay, great. So Shalini ma'am was asking that there are reactants, like different reactions are there, different reactions are there, the reactants would be different, the conditions could be different. So would the chemical kind of the energy of the reactions would also be different? So like for example, water is there, she took that example. If water is taking part in two different chemical reactions, so would the energy would be different or it would be same? So the answer is that for a substance, the chemical potential energy is same, because for a substance, for an atom, for a molecule, it comes from its orientation, its shape, its composition. But for a chemical reaction, the energy would depend on all the things. Whatever the reactants are taking participate into that, or the conditions, everything will play a role in the energy of a reaction.
Could you please again, could you please again explain what is chemical potential energy?
Okay. What is chemical potential energy? So shall we go to the slide or shall I just do it?
No, you can just explain.
Should I give a short answer to that?
Sure, Vanshula ma'am.
Dory, the positions of atoms have like we talked about atoms having attraction and repulsion between them, and the positions they take, because of which I mean they make formations, they come together or they go away from each other, but they make positions, they take positions, and therefore the potential energy involved in whatever position they have, that is the chemical potential energy. That is what she's calling as the chemical potential energy.
Got it. Okay, thank you.
Okay, great. So the question now is, the burning of a candle is exothermic or endothermic? And I have some answers in the chat already.
Exothermic.
Exothermic. Okay. We have one endothermic also, and then the melting is endothermic, burning is exothermic.
Yeah, it's both endothermic as well as exothermic.
Okay. But usually, if you will say that burning of a candle, it's giving you heat. There is light, there is heat, so it's kind of heat out energy. So we take it as exothermic reaction, burning of a candle or like any other fuel. But even to burn a candle or to burn any fuel, initially you have to give some energy. Like for example, here to burn a candle, we need to bring a burning matchstick first. And when it will catch fire, then it will start kind of burning on its own, and then the more energy it will be released, it will become a exothermic reaction.
To have the ignition temperature of the wick. Ignition temperature.
Okay, then there is activation energy. Okay, that's fine. So again, I will go to the most simple kind of at the most basic level. And let's see what happens in a chemical reaction, that even to start an exothermic reaction, we are giving some energy to start. So in a chemical reaction, what happens? Bond
Must be broken, then formed.
So formed.
First, we have to break some bond. Then only new bonds are formed. And for these bonds to break, so like now there are bonds which are stable. There is a system which is stable and we are breaking it. We are making it unstable, like more unstable. So if we make a stable system towards more unstable, how can we do that?
Making it.
Yeah. So if we make a system more unstable, or you can say less stable, it means we can add some energy to it. If it will have more energy, it will become less stable. So in this case, we need to add energy. So if we have to break a bond, we have to give some energy. Is this clear to everyone that if we need to break a bond, why do we need to give energy?
Yes, ma'am.
Great.
Actually, we are doing decomposition reaction by heating, ma'am. That is the giving nice example, I think.
So, ma'am, like you will see that. Okay, just wait. I guess a few more minutes, and then we will see why we are not taking specific reactions.
Both
Okay, just
need energy.
Okay,
Need
ma'am.
energy.
yeah. So let's.
Yes, ma'am.
So breaking bonds, they require energy. We have to give some energy if a bond has to be broken, and if the bonds are made, new bonds are formed, then energy. So based on like as we just discussed earlier, can we kind of have a similar explanation for making bonds also? That why the energy is released when new bonds are made?
In order to attain stability.
Sir, your voice is not clear.
In order to attain stability, ma'am.
Okay. So I guess I will just go with it, that now as you have gave some energy for breaking bonds, so now there is some energy which has made the system unstable. So now it is going towards more stable. It is making new bonds. It is going towards stability. So from unstable to stability, what will happen to the energy? If we are increasing the stability, it means
More energy from the system.
Taken off. Yeah. So with the two statements are, I guess, would be very clear that if we are breaking bonds, then the energy is required. If we are making bonds, then the energy would be released. Okay, great. So this energy, which is required to break bonds or which is released when this bond forms, it's called bond energy. This is here we have taken example, the fluorine molecule. If it breaks,
Preeti, I just want to make a small addition. See, if you ever forget that whether breaking or making requires energy, just think of two magnets which are tightly stuck to each other. To pull them apart, you will have to give energy. So, which means which is like breaking bonds. So the two magnets stuck to each other, but when they come together, they will release energy. I mean, you don't give energy, they will release energy when they come together. Remember, magnets will run towards each other. when they want to come together, they'll run towards each other, which means, and they will stick with a bang. So they will release energy. So just remember that picture in your mind so that this point doesn't get confusing. Yeah. Kritika.
Yeah. This is just an example. So if chlorine molecule is kind of its break into atoms, this much energy is required. So what if these atoms join again to form molecule? How much energy would be given out?
242.
Yeah. So the amount would
The
be
same amount.
Same amount of energy,
but
in negative sign.
So sign would be changed, but the amount would be the same. So be it exothermic or endothermic, both process will happen in each case. So like, is there an exothermic reaction? For that also there will be a breaking of bonds, making of new bonds. For endothermic also both process will happen. So then how we will differentiate between the two? Like we are giving energy, there is energy releasing also happening. Earlier it was very simple. If energy is released, means exothermic. If energy is taken, it's endothermic. But now we just saw that energy is given and is released in both the cases. Then how can we differentiate between the two? So let's do that with an example. So there is a reaction, hydrogen and chlorine, they are combining to form HCl. So in this reaction, which bonds are being broken?
Hydrogen and chlorine.
Yeah. So hydrogen, hydrogen and chlorine, chlorine, these bonds are being broken. And which are the newly formed bonds?
Hydrogen chloride.
Hydrogen. So two bonds are being formed of hydrogen chlorine and one bond of is being broken for the each of the reaction. So for this reaction, the total energy in and total energy out, if we will see, so total energy kitna, like how much energy we have to give? It's bond energy of hydrogen, hydrogen plus bond energy of ClCl. Okay. And total energy out means how much energy would be released. So which bonds are being formed will come from bond energy of HCl. And twice, like we'll multiply by 2 because 2 bonds are being. So this is a data table where you can find the bond energies of hydrogen, ClCl and HCl. So using this, we will have the value for this 3 bond energy. So these are, you can, if you have a paper and a pen, you can note down these. I'll just wait for a minute. For the reaction of hydrogen plus chlorine giving hydrogen.
Product side, we get more energy, ma'am.
So we will see,
Yes.
sir. Let's go
It's
step by
862. It is coming.
Okay. So I'm hoping that all of you have noted down this value. So now let's calculate total energy given in and the total energy which was given out. So total energy in, how much energy did we give for breaking of the bond?
678. 678, I think.
678. Okay. That's right. It's 678. And the total energy given out is?
862, ma'am.
862. That's right. So these are just simple calculations, the addition of the two values, and it will be multiplication of bond energy of HCl. So if now we calculate the change in energy, so that would be how much energy we given and how much energy was released. So if we take the difference of the two, what would be the change in energy?
184.
184.
Okay. So that is minus 184. So the minus sign again, as per sign convention, it is telling us that energy has been released. So it is an exothermic reaction. So if we see this exothermic reaction, then again, we have taken, this is the level of hydrogen and chlorine which were reactants. This is the energy level for these two. Then we gave some energy for the bonds to be broken. Then the energy was released for the new bonds which were formed to 2HCl. So the overall change, if you will see, that is minus 184. So for exothermic reactions, we can say that energy which is given, this is less then the energy which is released. So if you compare the two, and if more energy is released, so overall the energy is released, we can see, and exothermic. So what about endothermic? So here we have taken another example. There is ammonia is being decomposed into nitrogen and hydrogen. The data is given here. So you can simply calculate the energy change for this. I will just wait for 2 minutes and then we shall move forward. So you can take the bond energy of ammonia, which is like NH bond into that. Then for nitrogen, it is bond between N and N, nitrogen and nitrogen. And for hydrogen, this is the bond between hydrogen and hydrogen.
So that
In
is
the product side, the energy level is more.
yeah.
Just give
14.
me
The
the
difference is 1472.
okay. Just give me the final value, the final change in the energy.
1472.
That is the final, like given in minus, given out.
Ammonia NH3.
Is it 1457?
That is total energy change, ma'am?
No, difference, ma'am.
Yeah, the difference between the energy which was given and minus the energy which is given out.
The total energy does, I think, 2239 minus, minus 782. Then 1457 will be. Is it correct? Or I have to check?
If not, you can please.
I'm getting 1472.
1472. Okay.
1472.
Are you asking for the sign convention, ma'am?
No, sir. Okay. So I have not done the calculations on the screen, but I will just, I guess, let's go step by step. So for the reactants, we have ammonia, NH3. So in one molecule of NH3, there are 3 NH bonds. So in 2 molecules of ammonia, there will be 6 NH bonds. So for NH, we have 391. For the reactant side, we would multiply 6 into 391.
So, yeah, wrong calculation. Sorry, ma'am.
That's fine. That's fine. So I will suggest, like, you can, if you haven't done this, you can do that.
2376.
Yeah, 2376. It's 2346.
2346.
Yeah. So for the reactant side, we have 2346. Now for product, we have nitrogen molecule. So that is just N bond. We have simply N946. For hydrogen, we have 3 molecules. So 3 bonds between hydrogens are being broken. So we will multiply 436.
36, yes.
1308.
254 total.
154 would be the total on right hand side. And if you take the difference between the two, we will have minus 92 or 92 as I'm getting in the chat already from Shalini ma'am and Minish.
92.
Yeah. So the difference is 92. Shalini ma'am, if like here we are taking difference between what we gave. So we gave more energy. It was 2346. And what was released while the bonds were being formed was just 2154. That was less. So it will
Correct.
plus
Yes.
90.
Yes.
Yeah.
Yes.
So this is endothermic reaction. So now if we take a look at the graph again, if we have relative just the energy of the reactants in the product. So there were reactants, 2 molecules of ammonia. We gave some energy, the bonds were broken, then the bonds were formed, some energy was released. But the energy which was released was less than what we provided for the bonds to be broken. So overall, we had to give some energy. So for endothermic reactions, we can say the energy which was taken into break bond is more than the energy which is released in making. Are we clear with this? Or is there any confusion for exothermic or endothermic?
Can you repeat, please? Little confusion is there.
For both?
Regarding how we get 92 in that one.
Okay. How do we get 92? Can you kind of tell me your calculations, ma'am?
The same 782 gives 946 plus 1308. Then from where, how we get 92? That's what I need.
It is not that, no, because it is 3 NH bonds. So 3 into NH plus into 2.
Yeah.
NH.
NH3, ma'am, if you will see at a molecule of ammonia. So one molecule of ammonia has 3 bonds of NH.
Okay.
So one molecule has 3 bonds, so 2 molecules will have 6 bonds. So we have to multiply 391 by 6. That would give us 2346. Then for nitrogen product side, this is simply 946. For hydrogen, these are 3 bonds which are being broken. So we will multiply 436 by 3 and that will give us 1208. So on the product side, we have 2150.
Okay, ma'am. Got it. Thanks, ma'am. Thank you. Thank you.
Okay, great. So are we clear with this graph? Like how the endothermic reactions, the energy given is more and energy which is released is less. So with these, we can say that in both the cases, in exothermic or in endothermic, the energy is being given in, the energy is being released in both the cases. But if we compare the two, in the exothermic, the energy given in is less, energy given out is more. In endothermic, it is reverse. More energy is required, less energy is released. So overall, the energy is taken in endothermic. Great. So are we clear so far? Any confusion till now?
No, ma'am.
Okay. Okay, great. Nice. Okay. So far we have dealt the energy in physics. It was gravitational, it was magnetic. Then we came to chemistry. There was chemical potential energy. So now let's have something from bio as well. So where do our bodies get energy from?
The food what we eat.
Food.
Food. Yeah. So we get energy from food. Yeah. So how does food give energy?
It undergoes combustion because of respiration.
So breaking complex food into simpler ones where bonds are broken.
So we are breaking complex food into simpler ones and that's how we get energy. So it means we can say that breaking down food gives out energy. We are breaking down food and we are getting energy. So this page, it's taken from class 10th NCERT book. So if you will see over here, there is breakdown of glucose. Energy is released. If you will see on the same page, here it's written that phosphate linkage, which is a kind of bond. It is broken and then the energy is released. So we are breaking down and the energy is being released. In some case, you will even see that the energy is trapped between the bonds. When the bonds are broken,
Photosynthesis.
Yeah. Okay. Yeah. The answer, I guess, I've already got in the chat and from the star also. It's photosynthesis, from where the glucose is primarily made. Here also you will see that the energy, chemical energy, it is stored in the bonds of carbohydrate. And when the bonds are broken, the energy is released. This is from class 11 NCERT. So this is very common to come across. Manish Gulati ji, you want to say something?
No, ma'am. All good.
Great. Okay. So can we say, based on these kind of statements or what for this, that breaking down into smaller units, it releases energy. The food, the complex substances, the complex units, the bigger units, they are being broken and the energy is released. And if the cells are building the bigger units, the energy is required for that. Is it true or is it false?
True, ma'am.
It is true. Okay. So now we have two statements. The first one says that breaking bonds require energy, which we just discussed before this, that if we are breaking any bond, the energy is required. And if the new bonds are being made, the energy would be released. But now we are saying that breaking down into smaller units, it's releasing energy. And building up bigger units, it requires energy. So aren't these two kind of contradictory statements? One is saying breaking requires energy, making releases. Another is saying no, breaking down releases and the building up requires energy. Okay. So this kind of becomes confusing. If you there is like research also done where there were kind of college students who were asked these simple questions, and because we take kind of energy is treated differently into physics, chemistry, and bio, so the confusion comes from kind of these kind of statements. So if we don't have clarity at the basic level, okay, what is happening, things can become confused. So how do we kind of address that? So now if I ask how energy is stored and released in the life. Starch usually in the roots of many plants. Okay. So this is basically yeah, Dori.
Are you going to discuss about that contradictory statement?
Yeah.
Okay.
That's the whole point is of this, that yeah, because of the disconnect, the confusion comes, and how the energy is being treated. So let's kind of address this. So this is the equation for photosynthesis. We have taken like this, we kind of start reading it, we are getting in the books from the very small level, that this is the equation for photosynthesis. This is carbon dioxide, then there is water, there is light, and this light, the energy is kind of trapped in the bonds of glucose, is stored, and then when it is broken, the energy is released. But in actual, if you see, when kind of biology is taken at the high level by students, so they kind of go through this, that photosynthesis or any of these are not single chemical reaction. These are multi-step processes. So these are not like a single reaction, these are processes. So even like just this is just one kind of pathway for this. As you can see on the left side, I'm not going into the details of this. I'm not kind of a biology person per se, but you will see that these many steps are kind of required to make one of these pyruvic acid. So these are complex processes. Respiration, like this was example of respiration, aerobic, anaerobic respiration. Respiration is a complex process. Photosynthesis is a complex process. So this statement, if we come across, that breaking down bigger units releases energy, and building up, it requires energy. It's true for life processes, and each life process involves many coupled reactions. So, and in those individual chemical reaction or any chemical reaction, wherever it is, how is it happening, this is true for every chemical reaction. That if bonds are being broken, they will require energy. And if bonds are being formed, the energy would be released. So for every reaction which is taking place in kind of photosynthesis or respiration, many reactions are happening, but for every reaction this would be true. So there are no contradiction. This is just that we usually take photosynthesis as a chemical reaction, but it's not a chemical reaction. It's a process, a complex process. Stored as complex. Okay. A reverse of this reaction is fermentation, right? Abhinaya. Reverse of which reaction? Can you please put in the chat? So in the meantime, I guess we have discussed few concepts, and I'm hoping all of this is clear so far. So building up the
Yes, ma'am.
Great. So how does it help us? Let's go back to our campfire days when the humans, they used to gather around a fire. There were stones, there were fire. Okay, dancing is going on. What happened? Like, this is just a kind of imagination. Okay, they brought some rocks, some stone, they put into the fire, but they saw that, oh my god, after putting it in the fire, the color is changed. Now there is something else. It's not a stone, it's shining. And if they put up, oh my god, this is something that can be used for many things. So this is kind of how the metals could have been discovered. So this was just the simplest kind of extraction of a metal using fire. And that's how the earlier people, from where we started, that there were the metals which could be easily extracted, which could be easily broken down. They were like simple oxides were there. So simple compounds were there of those metals. You were just heated and those will be extracted into its components. But okay, it's something around us. It's a substance. It's around us since the beginning, still around us even now. We are heating it since, like, again beginning, maybe we are heating it again. So you are heating it, but still you cannot separate its components from heat. So can you guess which substance is it? It's very, like, everywhere is found. From the beginning it is. It's not a metal.
Sand, ma'am.
Sand. So do we heat sand like in daily life? You will be heating this substance also, sir. Everyone does it at their home.
Stone?
What? I'm not heating stone at my home.
Water?
Yeah.
Water.
So this is water. So every one of heaters, it is being done since like so many times, but still it does not separate into its component. In the chat, I'm having what do you mean photosynthesis is not a chemical reaction? Shalini ma'am, what I meant was that photosynthesis is not a single chemical reaction. It is a complex process which involves many reactions.
Somebody answered already. Thank you so much. Got it. Yes.
Okay.
Thanks.
Yeah. Okay. Coming back to. So if you will heat water, it will just simply get vaporized. From liquid, it will get converted to steam. So is it a chemical reaction?
No, ma'am.
No, it's
Since
not.
the chemical composition remains the same.
Yeah, it's still water. It's just in gaseous state. So if we provide heat, it means we are providing energy to water. So we are just kind of increasing the kinetic energy of the particles. The moment is increasing, like if we have done into kinetic theory. But it's not enough to break the bonds of water molecules to split it into hydrogen and oxygen. It will just get vaporized. So if you will see, to break one molecule or like a mole of water molecules, we need 890 kilojoules. And before we provide this much energy to water, all of it will get vaporized very much before it. Then how can we split water?
By passing current, electrolysis.
Yes, electrolysis. So by electrolysis, we can separate the ions, we can separate the water into hydrogen and oxygen. So the metals which were more reactive, the highly reactive metals, sodium, potassium, all of this were there even when like copper was there, iron was there. But these were not discovered because they could not be separated from their compound. So they needed electrolysis. They need more energy. And when electrolysis was introduced, then we could discover all these metals. So if you will have a look at this series, which we call chemical reactivity series, as you move upwards, the metals become more and more reactive. So as much reactive as it will be, the more difficult would be to decompose it. And the ones which are like at the bottom, they usually occur naturally, no chemical actions needed. As we move upward, their bit of energy is required. You will have extractions method based on that as move you further. So now there is whole kind of branch for metallurgy, for extraction that do this. Okay. So this reactivity series, how it can help us? It can help us deciding the best way. This is just kind of relative reactivity. So based on the position of the metal in this series, we can decide what would be the best way to extract the metal. And it can also help in this displacement, which metal can displace the another. Like there are, if you go into research, there is a compound of a metal and you see, okay, this is some properties they are having. I want to change the properties a little bit. Can I use this metal also? So in those things, like this can also help. Now, if we talk about energy in chemical reaction, so if we know the energetics of a chemical reaction, it can help us to see and to decide whether a chemical reaction will happen or not, what will be the possible products, as I kind of did in my master's project, which product will be more stable, if there is another way to do it more efficiently. So these are just kind of things where the energetics come into place. Now, this is the question for all of you. Like for endothermic reactions, the products have higher energy. It means they are unstable than reactants. Reactants are more stable. They have less energy. But products, they are having more, means they are unstable. Still the reactions are taking place. So what is making these reactions possible?
Maybe the entropy value will be higher than that of this enthalpy, ma'am.
Yeah. So for these chemical reactions, if you really want to get it, so energy won't be the only factor which will be deciding their enthalpy, their entropy, as there has there. So there are many factors that comes into play when we kind of go into the feasibility and everything. And based on these, we have different kind of branches. There are thermodynamics, there is kinetics, there is metallurgy. So this all of this can be discussed over there. For this session, we just went for the energetics, the simplest one, which we can kind of open up for the students, and maybe some confusions can be cleared up. This was all from my side. If you have any questions so far or any comment, you can put in the chat or you can unmute yourself. In the meantime, Shalini Sharma ma'am has asked in the chat, what makes zinc 30 protons more reactive than copper atomic number 29? Both are in the same group. Shalini ma'am, like
same period, sorry, not group.
Yeah. So yes. Copper and zinc, as you said, are not in the same group. They are in the same period. So what makes zinc more reactive than copper? Okay. So for reactivity, I would say like when we do the periodic table, I'm kind of in the process of making a session for that also. So many things come into play. One is as you move towards the right in the periodic table, the size is increasing or decreasing, Salima?
Ma'am, it is decreasing. See, I know the concept, but here, if you go by the concept, zinc has only 29 protons, while your copper has 30 protons. Okay, and the shielding effect is also constant. So by this understanding, zinc should be far less reactive than copper, but it is the other way around. Zinc is 30, higher nuclear charge than copper.
Yeah, it has higher nuclear charge than copper.
So then,
I guess there are like many factors. The electronic configuration also, like if you will compare like this, there are sodium, which is on the left side. This is just one electron. And towards the right, if you will say there is fluorine.
Electronic configuration also, if you see, then zinc has fully filled d orbital. It is 3d10 4s2. while your copper is 3d9 4s2. Okay, so copper has a vacant d orbital as well. So what I have still not been able to figure out, I've asked many people honestly. Okay.
Okay.
So yes.
So at the instant, so I will just think about it. So I don't
Thank you
have,
so much. Thank you. Yes.
but I will surely get back to it because yeah, like many factors come into play. How, as you said, like configuration wise, it should be less reactive, and as per the nuclear charge also. So yes, but I will check on it and then. Any other questions regarding the energetics that we discussed today?
A lot of people are saying thanks to you, Preeti, and also Manisha has for everyone. Manisha has put in our links. Actually, she has put in our YouTube channels. We have like okay, this session is also going on a YouTube channel, which is Joy of Learning Sessions, and then there is another YouTube channel which has short videos. Well, in fact, we are starting another one in English. So short videos in Hindi and short videos in English. We are trying to put content in various forms. So for that, please see the links Manisha is posting. And meanwhile, Preeti can take people's responses.
So far, okay. So I'm quite glad that it kind of went quite well. It happens when we do participate, and it is a very foundational topic. Yeah, the concepts are very simple, which all of us have already like read. Not this, but much more into enthalpy, entropy, and whatnot. But when I was designing this session, it kind of brought all the streams of science together. There was physics, there's chemistry, and then biology. So even for me, it was a thought exercise. How do we, for students, how do we all bring it together so that the confusions can be cleared up? Ravi has raised his hand. Yes, Ravi.
Ma'am, I want to ask the question. What is energy?
Ravi, in a very, very fundamental sense, movement is energy. I mean, in our whole world, whole universe. My husband is shouting from behind that potential energy is not moving. We have just explained the relation between potential and kinetic energy. So I can only. Oh my God. Now, my husband, without listening to the session, now he's jumping. But yeah, actually, if you ask me, I'll say movement is energy. Otherwise, friends, please look at the resources Manisha has put in. And also, we don't have a separate WhatsApp group for chemistry teachers, but we are trying to we work on chemistry, physics, and biology, and even environmental science. So all the 4 sciences currently, and a little bit of work on math is also starting. And actually, we have covered most concepts till 10th, and now we are moving towards +2. So it's a slow journey where we work on individual sessions and or topics or concepts and keep working on them. And slowly, we are trying to build in complexity. And since most of you are chemistry teachers, Preeti is indeed working on periodic table right now. We figured out structure of periodic table where you can make children fill up the periodic table by themselves. So which I think would be a very nice thing to do. But then after that, the interpretation of periodic table, which Preeti is working on. So we'll keep offering more and more as we go along, but also in physics and biology. And actually, these English only sessions have started only now. I mean, we did some during COVID, but now because we have a group like you people who are coming, who like many people from the southern states and other states are joining.
Excuse me, ma'am. Actually, I am a regular follower. Actually, in previously, I think during December, we had more concept only in English. After that, most of them are in Hindi. That's why I couldn't continue with you. And after a long time, it is again back in English because we are expecting more in English.
Lalita ma'am, we'll try to offer in both because our primary target group. I mean, so far we don't have so many relationship with teachers in states where people are non-Hindi speaking. And in fact, there's like some people who continuously follow us in the Hindi belt, and that's why we offer more in Hindi. But we'll try to keep both alive. I mean, to the extent we can.
Actually, it's a long gap for me. Actually, I'm regularly following. After the mole concept, it was there. After that, I didn't get. Everything is in Hindi. Hindi is coming. We are not feeling so much with understanding with Hindi. So I'm looking for that, and today we get it.
And Lalita ma'am, there was acids and pH also. pH, acids and bases, but you probably missed it. It was in English.
Really? I didn't. It's in a WhatsApp group. I'm there.
But you can actually check on the our YouTube channel. So there'll be a recording of that webinar. So all webinars are recorded live. So that is there. And Manisha is keeping track of all the people who are present right now. Manisha, do you need any details from people here? I mean, people who are present.
We need to put our school name and all, ma'am, or no need?
If you don't need, then I think we'll just put your name.
Okay, ma'am. Thank you, ma'am.
There's a Google form that we have to fill.
Feedback form. That's a feedback form. It will be nice if you can give us feedback and also give us suggestions on what topics you want. You want more than others. So that will also help us kind of plan. There are always some topics in the pipeline, but if teachers raise some demands or expectations, then we can maybe work in those directions. Shalini Sharma ma'am has raised her hand. So you want to say something?
Yes, ma'am. First, I must compliment Preeti ma'am. Very subtly done, because and the scaffolding was very, very beautifully done. Because see, honestly, I teach the senior classes. Okay, so for me, at times I really struggle to get the basics clear to the students. Okay? So this session definitely helped a lot in that regard. I have a question for Preeti ma'am, because this is equally confusing for me as well. Okay, I understand this is all the ball game of the charges. Okay, we say bonds are formed because this attracts, that attracts, right? My question is very simple. What is a charge? You say electron is negatively charged, okay, but what is a charge?
Preeti, you want me to answer that?
Anybody, I'm dying to get this answer.
Anshuvala ma'am, I guess he has the best answers for these, the basic ones. What is energy? What is charge? Say, Anshuvala ma'am, please go ahead.
Yeah, so actually charge is a property. Now, it's a property which typically lies on masses. And I mean, if you see that, I mean, an electron having such a little mass can have the same property. I mean, as much of charge as a proton, which is so much more massive. So this property has got nothing to do with how much mass is there, but it's a property which actually matter carries. So, I mean, and why this property exists or why charges attract or repel each other is something we cannot answer, because it's like our world is given to us with these properties, these fundamental properties. So in answer to Ravi's question also, I said we have these four foundational forces on which our world is running. So electromagnetic forces, gravitational, and nuclear forces, and which one did I miss? But the thing is, it's like charge is the property which allows matter to attract or repel. I mean, like charges repel and attract, or the electromagnetic forces occur because of charges. So, I mean, other than that, we cannot actually define this property or this thing that we call a charge. But it's like I mean, you can equally ask the question, what is mass, or why mass?
Absolutely,
But then,
yes.
So these foundational ideas actually is, you can say, these are the givens of our world. I mean, universe gave us these, and we are, when we study behavior, we have to see what our universe is made up of and what kind of interactions we have amidst whatever constitutes our universe. So more than that, I do not think you will find an answer to a question like that.
Thank you so much. Thank you.
Welcome.
Ma'am, the Google form has a provision to write the school name. Is that enough?
Yes,
Anisha will answer this question. Manisha, Google form must be the feedback form, isn't it?
Yeah, it has. Yeah, the feedback form has a provision to write the school name also there. There's a.
Yeah. So you can write if you want. I mean, see, feedback is more for our use.
No, is that enough for the certificate also?
Yes. Like I said, the certificate can be only with your name, but if you want your school name, yes, we can put in your the name of the school if you want. Otherwise, it will be just your name.
Ma'am.
Yes, Ravi.
I can't satisfy with your answer that you said that movement is energy. Then the second question is entered in my mind is that what makes the things to move? And then I finally answer self by the force that we applied. We applied force and it will move. And similarly, the answer you gave me that the movement is energy, then this is energy, and this is wholly get into a cycle. And I am in confusion to how to differentiate between energy and the movement.
See, what I'm saying is that like I'm saying, movement is energy. So and energy keeps taking different forms in all forms. In all forms, actually, there is movement of something or the other involved. Or like in potential energy, we said it leads to movement. But when it comes to force by itself is not energy. When force makes something move, when force causes movement, you've read the definition of work. Work is force into distance. When force causes movement, then it transfers energy. Like force, you can say, is the agent which makes transfer of energy possible between two things. So if you are applying the force to a wall and no movement happens, no energy transfer happens. But the moment your force will make the wall move, suppose the walls gets you are like an elephant and can make the wall move, then there'll be energy transfer. So force is the agent which transfers energy when it is able to move things. But energy by itself is movement. Because kinetic energy is just movement, half mv square. That's it. And then all other energies can convert into kinetic energies and vice versa. So my energy just keeps changing form.
I also can't get my answer of the question that I asked in the starting of the session, that everything wants to be unstable, and the thermodynamics second rule said that entropy of the universe will always increase. So how the rest is the natural or tendency of an object, or why not movement is the natural tendency?
It is the natural tendency. Rest is not the natural tendency. In fact, Newton's first law tells us that only. In fact, rest is just a special case. I mean, but there's no in the whole universe. There's no rest. Nothing is at rest. Everything is moving with relative to something else. There's always relative movement going on. Ravi, we'll discuss this separately. I mean, we should wind up this and close this session. You are getting into physics.
Just on a last note, I think entropy changes lower down the system. There's movement. So movement will have to bring down the energy of the system. And that is why it is favored. This is what I understand.
I don't know what actually Ravi is leading to, but I mean, I would want a more elaborate discussion on this. Entropy is not a simple idea, but yeah, it's a very, very important idea, because I mean, beyond a point, then entropy decides everything. But like I was saying earlier, entropy, we have to deal with entropy of the full system.
Agreed. What isn't the chemical reaction, the system in itself?
Yeah, it is. Then you have to like, see, when you're talking about a full system, then you have to you have to ensure that it's if you are making only energy calculations, then you have to ensure that no energy is coming out from outside or going out of that system. Then you can make the total energy calculations.
No, but then if it is an adiabatics process, then of course energy will automatically be removed and going out of the reaction. It stays within, but then it will be out of the system per se. So then the whole thing again changes. Yes. Ma'am, I think we'll have another discussion if you can create a way, because others would also be in a hurry to leave. But yes, these are the questions that I would love to have answers from people of your caliber, please, anytime. So if a group can be created where we can freely exchange ideas and thoughts and these information, please, I'll be very grateful. Thank you.
Yeah, sure. Manisha has put in the WhatsApp group, the link for the WhatsApp group. So actually, that WhatsApp group is our announcements group. It's, JLF community, where many other groups are also part of it, where we actually announce our upcoming sessions. So if you are not there, please join. If you want to attend future sessions, then you'll have to join that to get information. So, Manisha, can you put it once again? Yeah, Manisha has put it once again. Please copy this link and join that WhatsApp group, so that you get information on all we normally put in every session that we are going to offer. And we will also put our YouTube channels there, so that people know. And we are trying to put in YouTube videos more. These sessions are all stored live there. They are streamed live on one of the channels, but on the other channels also, we are trying to put in short videos, which will be helpful for teachers. Normally, there's an experiment or a classroom activity, and there's explanation along with that. So with that, I think we should end, right?
It was a great session, I would say, quite good participation and discussion. Thank you, everyone.
Yeah, thank you, everyone.
Thank you, ma'am. Thank you.
Yeah, see you next time.
Yeah, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Yeah.